in this screencast, I will be teaching you about the different types of reactions. So in this class, you will have to be able to identify the type of reaction based on the reactants. You'll have to be able to predict the products and then write and balance a formula equation. So the first type of reaction is a synthesis reaction, and it's exactly what it sounds like. A synthesis reaction has two elements combining to make a compound. So if you're looking at the reactants only, then the reactants would be one element being added to another element. So that's how you would identify it. The generic equation for a synthesis then would be A plus B making AB. So element A, whatever it is, combines with element B to make the compound AB. So these examples that I'm doing are all in your packet on the guided notes pages. So if you look at page 17, that's where these two examples are. So the first thing you need to be able to do is predict the products in words. And the product will be an ionic compound for when you have to predict them. So you need to make sure that you're writing it with the correct ending. So this wouldn't be sodium chlorine, it would be sodium chloride, because that's how we write a formula for an ionic compound. So in your reactants, you have two elements. So remember, if you have elements, you have to check the back of your periodic table to see if they're diatomic or polyatomic. Sodium is not, so I'm just going to write the symbol for sodium, but chlorine is diatomic when it's an element by itself. In the products, this is an ionic compound, so you've got to make sure you check your charges and have enough of each ion so that their charges add up to 0. Sodium has a +1 charge, and the chloride ion has a -1 charge, so then the formula for sodium chloride is NaCl. You should never have charges in your final answer. If you put charges on your final answer, I will mark it wrong. A compound, when the two things are bonded, is neutral, has no charge. Then you've got to go back and balance the equation by putting in coefficients. In the second example then, magnesium plus phosphorus, again, make sure you change the ending to what it should be, so magnesium phosphide. If you check the back of your periodic table again for diatomic and polyatomic elements, you'll see that magnesium is not listed there. So you would just write an Mg, but phosphorus is polyatomic when it's an ion, when it's an element by itself. So phosphorus element is not just P, it's P4. Then in the products, you need to check your charges. So magnesium has a +2 charge, phosphide ion has a -3 charge. So the formula for magnesium phosphide is Mg3P2. Now I've got to go back and balance the overall equation. You've got 4 phosphorus on the left, so I need 4 phosphorus on the right, which gives me 6 magnesium, so I need 6 magnesium. The second type of reaction then is a decomposition reaction. A decomposition reaction is pretty much the opposite of synthesis. It's taking a compound and breaking it apart into its elements. So when you're looking at the reactants, you're going to see one compound, one single reactant in a decomp reaction. So the generic equation is just the opposite of synthesis. So you're breaking apart a compound AB into its elements A plus B. So these two examples, again, are on page 17 in your packet. So when you see one reactant, that's your clue that this is a decomp reaction. So you're going to break up that decomposition reaction into the two elements that make up the compound. Chlorine is not written chloride. Chloride is the ending when it's in a compound. When it's an element by itself, it's just chlorine. So over here you've got an ionic compound, so you need to check your charges. So you need 3 chloride ions for every 1 aluminum to make sure the charges add up to 0. On the element side, you need to look on the back of your table and check for diatomic and polyatomic elements. Chlorine is diatomic when it's by itself. And then I'm going to go back and add coefficients to balance all of this. In the second example, you have a compound made of phosphorus and chlorine. So this is phosphorus plus chlorine. Diphosphorus tetrachloride, that is not an ionic compound. That is covalent, and you know what the subscript should be based on the prefixes in the name. So diphosphorus tetrachloride is P2Cl4, and that's going to break apart into phosphorus, which is polyatomic when it's an element, and Cl2 when it's an element. So again, if you see elements in any of these equations, you need to check the back to see if they're diatomic or polyatomic. And then you've got to go back and add coefficients so that the whole thing is balanced. The next type of reaction is a single replacement reaction. In your packet, it says something about the activity series. Don't worry about the activity series. We are not going to cover it. So in a single replacement reaction, the way you identify that type in the reactant is by the fact that you will see one element and one compound reacting. There are two types of generic equations for this. So one equation is for when the element is a metal, the other equation is for when the element is a nonmetal. So if I call my metal A and the compound B C, what happens in a single replacement reaction is that the element trades places with one of the things in the compound. If the element is a metal, then it's going to trade places with the first thing in the compound, which is also a metal or a positive ion. So then in your products, you're going to have B by itself and A bonded to C. If the element is a nonmetal or a negative, if the element is a nonmetal, then it's going to trade places with the nonmetal in the compound, which is always the second thing written in the compound. So then you're going to end up with C by itself and B bonded to A. So you've got to check whether the element, the thing that's on its own, is a metal or a nonmetal, and that will tell you what it trades places with. For this type of reaction, I would highly suggest that you write the words out first. So in this first example, which is on page 18 in your packet, sodium is a metal. So sodium is going to trade places with the first thing listed in the compound, which is aluminum. So over here, you're going to end up with aluminum by itself and the sodium bonded with the chloride ion. Sodium is Na. Aluminum chloride has a formula of AlCl3. Because aluminum has a positive 3 charge, chloride ion has a -1 charge. And then over here you've got aluminum by itself and sodium bonded to the chlorine. Sodium has a +1 charge, chlorine has a -1 charge, so you only need one of each. And then you've got to go back and balance the overall equation. In the second example here, fluorine is a halogen. It's a nonmetal. So fluorine is going to trade places with the nonmetal in the compound. So over here, you're not going to have bromide anymore. The name of the element is bromine by itself. And then you've got calcium fluoride. Both fluorine and bromine, when they're by themselves as elements, they are listed on the back of the table. They are diatomic. So you guys really need to make sure that you're checking all of this. You are going to have to know all of this for your test next week. Calcium has a +2 charge when it's an ion. Bromide ion is -1. So I need 2 bromines to cancel out the charge on the calcium. On the product side, calcium still has a +2 charge. Fluoride ion is also -1 because it's also a halogen. So you need 2 fluorines to balance out the charge on the calcium. The elements do not have charges on them. The compounds do not have charges on them. Okay. You only need the charge to figure out what the formula is. The next type is a double replacement reaction. The way you tell it's a double replacement reaction just from the reactants is by the fact that the reactants will always be two compounds coming together. So if I have two compounds A, B, C, and D, in a double replacement, the first two things listed in each compound trade places. So then on the product side, C ends up bonded to B, and A ends up bonded to D. The examples for this one are also on page 18 in your packet, okay? So if you have a transition metal or a metal with a Roman numeral, that Roman numeral goes with that lead, in this case, to the other side. So in this double replacement, I'm going to flip-flop aluminum and lead 2. So in the products, you're going to have aluminum carbonate plus lead 2 oxide. Lead has a +2 charge. Carbonate from the back of your table has a -2 charge. Aluminum has a +3 charge. Oxide ion is -2. Whatever charges they have in the reactants, they're going to have the same charges in the products. So this formula is going to be PbCO3 plus Al2O3 Al2CO3 3. Aluminum is +3, carbonate is -2 over here, lead is +2, oxide ion is -2, so this is just PbO. So now I've got to go through and balance my overall equation like that. In the second example, you have lithium and barium trading places. So here in the products, you're going to have barium sulfate plus, no, sorry, oops, messed up. You're going to have barium chloride plus lithium sulfate. Okay. Lithium has a +1 charge, chloride ion has a -1. Barium has a +2 charge when it's an ion, sulfate is -2. So lithium chloride is just LiCl because the plus and minus charges already add up to 0. Same thing with the barium sulfate. +2 and -2 already add up to 0, so you only need one of each in the formula. Whatever charge each ion has in the reactants, they will have the same charge in the products, but you've got to rebalance the charges. So over here, because barium chloride, barium is +2 and chloride ion is -1, you need 2 chlorides to balance out the charge on the barium. And then in lithium sulfate, lithium has a +1 charge, sulfate has a -2 charge, so you need 2 lithiums to balance out the charge on the sulfate. The last type of reaction is a combustion reaction. And combustion reactions are actually pretty easy because 3 of the 4 parts of the equation are always the same. So my generic equation and identification are going to be sort of linked here. So the way you identify a combustion is that the problem will say combustion in it, just like the examples below. In a combustion reaction, you have a hydrocarbon, which is a substance made of hydrogen and carbon, or sometimes hydrogen, carbon, and oxygen, reacting with O2, oxygen, to make carbon dioxide and water. These 3 pieces of this equation that I'm double underlining never change. So you have to memorize for a combustion reaction that the second reactant is always O2 and the products are always CO2 and H2O. So in my generic equation, your first compound's either going to be something with carbon and hydrogen in it or something with carbon, hydrogen, and oxygen. And then your reactant is always, the other reactant's always CO2 or O2. The products are always CO2 and H2O. So on page 19 in your packet, the first two examples are there, but I wanted to give you one also that had oxygen in it. So if I see this word, I know that my second reactant is O2. My products are CO2 plus H2O. So I need a 2 here to balance the hydrogen, which gives me 4 oxygen on that side, so a 2 here. Second example, C3H8, giving you O2. So the second reactant again is O2. So this one, I need 3 here to balance the carbon. I need a 4 here to balance the hydrogen. 3 times 2 is 6, plus another 4 oxygen is 10, so this has to be 5. This third example is not in your packet, okay? In a combustion reaction, you can also have that initial reactant with oxygen in it. Okay. So I have 6 carbon on the left. I need 6 carbon on the right. I have 12 hydrogen on the left. I need to put a 6 here, so I have 12 hydrogen on the right. Total on this side, you now have 18 oxygens, but over here I've got oxygen in 2 places. So I already have 6, so 18 minus 6 gives you 12, which means this needs a coefficient of 6 also. So those are the 5 types of reactions that you're going to have to know.